Hello and welcome to this new coding series. In this series we will code a 3D rotational cube in C. So we have a cube, something like that. And by dragging the mouse or typing some keys, we are able to rotate this along whatever axis like that. So we're actually going to code a three-dimensional graphical application in C from scratch. So let's create a new file. I'll call it cube.c, and we can include standard IO here. We always need standard IO for whatever. And also we are going to use SDL2, which is a graphics library. Well, it at least allows us to create a window and interact somehow with the keyboard and the mouse. So let's start. I will start using a main method. Maybe let's do the standard way and return integer. And then we have to initialize SDL using a flag, and we have to indicate that we are going to use the graphics output and that we're going to create video. I think we have to pass something here that is, it's this initialization flag. So if you want to create an application that outputs video, some graphics, then you pass this flag. If you also want to pass or create sound, then you also pass the audio and whatever you need. So the first thing we're doing is we're going to initialize SDL, and after that we have to create a window. That is going to be an SDL window. How do I know all of this? Well, I have so far created two series on SDL coding. In the first one we did a Pong clone, and in the second one we did an implementation of the game of life simulation. So I'm trying to do this from the top of my head here. And if I don't know something, then I will look it up. So we create a window and we pass, if I remember correctly, dimensions, but let me just open the documentation here. So this is the SDL2 documentation, and we can open the complete API and do Control F, search for window, because we create a window. And as you can see here, we get an answer, a return value that is a window pointer. And we give the window a title, XY, width, height, and flags. So window title is going to be 3D cube. Then X coordinates are going to be, and here's something interesting. We can just pass this flag, SDL window pos centered. This will center the created window on the screen. Window pos centered. Same for the Y coordinate. Interestingly, you can use the same flag for both X and Y. Then we create a width of the window. Let's choose 900, and a height, which is going to be 600. And I know you can't see this right now because my camera's in the way. So let me just adapt this a bit. Now you should be able to see the code properly. Okay, and then what's missing is additional flags. We don't need any of those. Then we need to introduce, or we need to, probably we can also already check whether the window is created. We also need to introduce a delay. Let's do 5 seconds, 5,000 milliseconds. And here in the bottom right pane, I will compile what the code we've just written using CC and using some compilation flags. These flags, I don't just include them magically here. They are defined, or they are specified in the SDL introduction in the official documentation. So it's not like I pulled them from thin air. So let's compile cube. And that worked. And if we execute the application, we get a window with a title 3D cube. So that is already quite cool. And it's a good starting point. But now I would like to draw something to that window. And to do that, we have to retrieve the window surface. To do that, we can do this. And there should be some API method that retrieves the window surface somehow. Let me look that up. And by the way, let me open the application again. So this entire thing here is the window, and the black area is the surface. So, and to draw to the black area, to the, well, drawable area, we have to somehow get access to the surface. So let me just see. Yeah, there's the get window surface method, and we can pass the window, and then that's it. So STL get window, STL get window surface. And then we pass the window. And that should be it. We can then draw to the surface. And let's just do an example. We can create a rectangle, rect, in STL using that. This is just a structure, and we will initialize this at those coordinates using this width and this height. And then we receive a rectangle, and we can draw that rectangle to the surface using STL fill rectangle. We pass the surface and the rectangle, I think, and I think we have to also specify the color. And let's draw a white rectangle, FF. And maybe we have to pass the address of the rectangle here. Yeah, and then we have to do STL update window surface. Let's update the window here. And let's see if we see the rectangle. No, we don't see the rectangle because I haven't compiled yet. Okay, and there's our small little rectangle. And this is going to be the basis of our future 3D cube. Well, because we're coding everything from scratch, this is now the outline. We have shown that we can initialize a window, we can draw to a surface. But now I would like to create my own graphics functions. And one of those is going to be set pixel or draw pixel. Or maybe more generically draw point, and we draw a point to a surface. STL surface. And then we fill the rectangle, or no, then we provide the coordinates, because after all, the 3D cube is going to consist of many, many points, and they are scattered in the 3D space. So we have to specify X, Y, and Z actually. But here, this is still going to be a plain graphics function. So I'm going to draw a point to the two-dimensional surface for now. Later we have to convert the 3D points that we want to draw to 2D coordinates. So this is going to be the tricky part. So let's specify X and Y. And then inside draw point, let's do, well, we can just reuse that rectangle, fill rectangle code here. And the rectangle is going to be the pixel that we set. Although it's going to be set at the provided x coordinate, then at the provided y. And since we're just setting one individual pixel, we will set the width and the height of the rectangle to 1. Okay, let me define the color white. That is going to be UN32, which is a data type coming from SDL. That is color white, and that is that, so we don't hard code the color here. Okay, right now it's not drawing anything. Why? Because we're not calling the setPixel function. So let's do that. Let me call draw point here. We're going to draw to the surface, and we're going to draw a single point at coordinate 30, 50. I'm not sure if you are going to see this, because this is just a single pixel, and on YouTube you're watching compressed video. Yeah, there's a single point. It's probably invisible to you. So we're not going to draw such small points. We're going to make them a bit bigger. Let's just set them to 5. But I think we need a global variable, int point size, and that is 5. That is probably, if we draw a lot of points, going to end up in a very pixelated result, but we can check that later. I just want to make sure that you can see the result on video. Okay, and there's our small point. Now, what happens if we draw a line? Well, for a 3-dimensional cube, we're going to have to draw lines, because we're going to draw this wireframe here. Oh, actually, we also want these lines in the background. We're going to draw lines. I'm not sure whether we're going to focus on just creating individual points, or if we need a method to draw a line. This is going to be a bit tricky. Maybe we have to stick to points for now. And then maybe we also need another method that creates a 3-dimensional point in space. So let me just figure out what to do next. So we can draw an individual point. Next step would be maybe to define a coordinate system, because we are drawing a 3-dimensional cube, and I would like a coordinate system to go right through the middle here. That's not looking good. And this point in the middle of the screen is going to be 0, 0, 0. So 0x, 0y, 0z. And then based off that coordinate system, that transformed coordinate system, we can rotate the cube. Yeah, probably we have to figure out how to draw points in that reference, in that 3D reference coordinate system. So I would like to create a new method which accepts 3 coordinates, x, y, z. And then it will draw that point in this 3D space. And that what makes it difficult is that this 3D space is shifted. The original surface is this one right here, and we have to transform this 2D coordinate system to this 3D coordinate system. Let's do it like that. Yeah, so this is yeah, let's see how we can do that. So let's just specify a method. Int draw point 3D. So this is going to be the interesting part now. We're going to still draw to this. No, we're not going to draw to the surface because no, we're going to draw to the surface. We're going to draw to the surface and we're going to draw to X, Y, and Z, but those are not the same. Those X and Y are not the same as these X and Y. These are the X and Y in the 3D coordinate system. So let's figure out the based off the given 3D X coordinate, we have to derive a 2D X coordinate. For example, we say we want to draw this point here in 0, 0, 0. Then we know that the X coordinate must be shifted to the right. Maybe we need a new global constant that is a 3D or coordinate, 3D coordinate system X or offset X. That is equal to, I want it in the center of the surface actually. So we can extract the width of the surface or the width of the window. And let's call that the screen width. Screen width and the screen height. And since, yeah, okay, let's just define them. Int screen width is 900. Int screen height is 600. And I would like the 3D coordinate system to be in the center of the screen. So screen width divided by 2. And I would like, is that not allowed to have a, yeah, of course. It's not allowed to have a number as the first letter in a variable. But anyways, let's just call it coordinate system offset X. And then let's create an offset Y. That is the screen height divided by 2. So that is X in the center of the screen and Y in the center of the screen. Okay, I think we need those two. And for the Z coordinate, which is practically the depth, we might have to do something different later on. But let's just see if we can transform the X and Y to 3-dimensional, or from 3D to 2D now. So we received the X, the 3D X coordinate, and we add on the offset. Technically, we could do some matrix multiplication, transform something here. No, not multiplication. Multiplication is not used for offsets, but it's going to be a vector. But there's not, okay, no, it's not necessary. Unnecessary complication. So let's do X offset and then int Y 2D is Y plus coordinate system offset Y. Okay, and then we can draw the point on the surface using X 2D. So this is basically the transform coordinate of x and y 2D, which is the transform coordinate of y. And of course we have to, what do we do with z or z? We can figure this out in a couple of moments. Let's see how we can draw a 3D point now. For the coordinates, let's say 0, 0, and 0. This should give us a point in the center of the screen. Something is still wrong, of course. Coordinate system offset x is equal to screen width divided by 2. Initializer element is not constant. I've never used these defines before, but it might be time to get used to them. Let me just look up how they exactly are to be used. Define in C. I'm not sure if we use the equal symbol. No, we don't. Define Okay, let's see if that works. It did work, surprisingly. I was not sure about these divisions here. And apparently we have a point in the center of the screen, which is a good thing. We're ignoring the z coordinate right now. I am not sure if we should keep ignoring it for now. It depends on how we project the 3D point onto the 2D surface. That's interesting. But let's see. We are drawing a 3D point now. How about we draw should we draw a 3D line? No, I would like to keep everything as points, because this is probably easier to rotate using some rotation command than later on. We're drawing a 3-dimensional point. Then we need to draw more points. We somehow need to define all the points which make up the 3-dimensional cube. But to do that, we probably have to define lines and then sample the lines to get points. Let's create a new method. That returns. Would a structure make sense? A structure called point, and then we keep the x, y, and z in there. I think it would make sense. I forgot how structures are defined. Struct in C. Of course. Okay, so this is a three-dimensional point. A point consists of x, y, and z. So we draw a point. Like this, and then we call point.x and point.y, and that should be it. Unknown type name point. Did you mean int? Why is it unknown? It's up here. Of course, I have to say that this is a structure. Okay, let's see if the method still, or no, we have to fix it down here. We have to initialize a struct point that is equal to 0, 0, 0. And then here we have to specify that we want to pass the point. So we still have the point at the center of our screen. Yeah, great. And now I would like to do something like a point array, cube points, and that contains all the cube points. So let's generate a cube. Yeah, or initialize cube. Let's do that. And then we can draw all the cube points for every maybe we have to know the length of that array somehow. Okay, let's try to do that. And then we're going to loop over the point array, and we're going to draw the points in three dimensions. Expected identifier, what? Why? Do I have to wait. C struct array. Oh. Maybe here. Okay. Then let's create the method struct points. Create or no, generate, what was it? Initialize cube. Initialize cube. And here we have to specify, let's just hard code this. Number of points. We're going to have 300. Let's do 100 points. Then we create a new point array that is going to be struct point points. That is an array of size 100. We can fix this later on, of course. And we're going to do a loop for I and I equals 0, I smaller than 100. No, I smaller than number of points. And then we're going to fill the first or any point here. We're going to create the structure. And let's just say we put in I, and I. So we get a line that is increasing along all coordinates in 3-dimensional space. And we return that points array. I'm not sure what that error here is. Is it maybe a struct array point? No. C return array of structs. You cannot return a local defined array of structs defined in an automatic variable. What? Okay, let's forget about that. Let's not return things. Let's just do a void here and initialize the cube based on a struct. Based on the array here and the number of points. And that should work actually. Except down here we need to adapt this and pass an array of points. Struct point array number of points. then we need also an int that is number of points here. Let's do 100. Something is still not well defined. Maybe it's this part here where I have to actually cast this somehow to the struct point, or to that. No, what is the error? Initialize cube. Invalid initializer. We don't get a return value. Probably that's the issue. But that is expected because we laid out the function like that. Okay. And we still draw, it still draws only 1 point. Why? Of course, we're just initializing the cube, but then we don't draw anything. So I would like to create a new method maybe that draws multiple points. So let's copy that method to draw a single point, because we want to render the entire three-dimensional object. And we are drawing to a surface here. That is fine. And then we're drawing an array that has a length. And we can here, right here, wait. We can right here do a for loop for int I is equal to 0, I is smaller than length of the array. Maybe that length argument is superfluous. C for loop length of array. Size of array divided by size of array at index. Okay. Let's try to do it without the length. I always do it because the other ways are too complex for me. But let's try to actually do something and learn something today. So the array length is int array length is size of point divided by size of point, and then this first element. Array length, and then increment that. Okay, so here we have the point x, we need point at ix, and here we need point at iy. That draws the points. Conflicting types for draw point 3D is the error message now. By the way, the error messages are printed down here. Conflicting types for draw point 3D. What is the conflicting type? I will try to compile it anyways. Maybe I get more info here. Ah, there's the error. Conflicting types for draw point 3D. Oh yeah, of course, obviously, I have to rename that method to draw points, because we're drawing multiple points. Let's see if that can compile. No, of course not. Now we're getting the following error. Now this is just a warning that size of will return the size of the entire structure, which is fine. I mean of the entire pointer. Let's see if it executes. No. We draw the point, each and every point. Of course we have to initialize the cube, and then we have to call draw points now. And we have to provide all the points. And we can actually delete the first point just to not get distracted by it. So let's see. And now we have nothing. Why do we have nothing as an output? Draw points, size of on array function. Let me just do 10 here, just to see that this is not the cause. Oh, it is the cause. Now we get a small line. So that means that the size of is wrong. But what is wrong here? First of all, I will rename point to points. And then size of points. But then why is it working here? I think we need to study that error message here a bit better. There's a warning: size of on array function parameter points will return the size of struct point pointer. I will look for that message. Maybe it's not correct. When you pass an array to a function, its address is passed to the function as a pointer. Ah, right. As a result, okay, you can safely use size of array 0 only within scope of declaration of array. The array decays to a pointer when passed. Yeah, that is the issue. So this hack here doesn't work. Is there another method? There is no way to determine the length inside the function. Best way is to pass the number of elements as a separate argument. Okay. I thought I could learn some... Well, I did learn something actually. That my previous approach was good. Number of points. Then let's do that. So number of points here. And we draw the points 3D and pass number of points as such. So let's see if we can print the line. Yes. So this is our first line, which is a 3-dimensional line, although the Z coordinate is not yet considered. So this is a simple plane projection. Let me look up the projection types. Projection types 2D or 3D to 2D. Yeah, there are a couple of different projection types that we might have to consider. We have, I think, a parallel projection. I think using this isometric projection would be good, which is the classical projection that you also have and that you use in school right now. The projection we're using is pretty much this one. Coordinate system is like that. That is X, that is Y, and Z is going right in your face like that. So we still have pretty much a 2D coordinate system. Now how do we transform the 2D coordinates, or our current coordinate system, to this isometric projection? There are 8 different orientations to obtain an isometric view depending on which octant the viewer looks. Oh. the isometric transform from a point A xyz in 3D space to a point B xy in 2D space, which is what we want. Looking into the first octant can be written mathematically with rotation matrices as this one right here. Ooh. So do we have to implement matrix multiplication, or is there a better way to do that? What is the... we have a point in 3D space. Yeah. And then we have a point, or we want to project it to a point in 2D space. Right, okay, and then we have to project it to the xy plane using this multiplication here. Yeah, we will do that. Let's see, C matrix multiplication. Let's keep that open for later. Let's just define the point in our initialize cube. Or let's define the cube in initialize cube. So first of all, we need well, how many sides does the cube have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. So let's do points per side is number of points divided by 12. A cube has 12 sides. And then 4 points per side. I think we should have side 1 here. Let's also note them here. Side 1 is this one. Maybe we should create a method to generate points on a line. This is really not straightforward. Okay, the x coordinate of these starts at... Oh my god, this is really not straightforward. Initialize cube. So here we have to create the first side. The first side starts at x. Well, that all depends on variables, actually. The side length of the cube is, let's say, 100. Okay? So if we... So x should start at minus side length divided by 2, because I want it to the left of the axis. Then plus points per side. we have somehow to create a step size. Int step size is equal to side length divided by step size. No, divided by points per side. Plus I multiplied by step size. So that should give us the range from x, from negative x to positive x space. Y doesn't change. Y for the first coordinate is minus, for the first side is minus side length divided by 2, and z is also plus side length divided by 2. Let's see if we can draw that. Ooh, oh, that's horrible. But I don't see what would be wrong with that, actually. I mean, it looks okay for this part of the line, but why is it scattering points around the plane? Side length is 100. Let's change it to 50 and see what happens. Still weird. Points per side is number of points divided by 12. Yeah, maybe we have to somehow ensure that this number of points is divisible by 12. Nope. Maybe it's just because we are initializing one side, but not the other ones. So that's why they have unexpected values. So let's continue with side 2. And side 2 is going to be that side up here. It's pretty much the same, except the y coordinate is now in the positive y space. So let's see how that looks like. Doesn't look good. Why? Because we are looping at I equals to 0 again. We have to start at an offset now, at points per side. And then we have to go until 2 times points per side. Okay, now we have 2 lines, but they look weird. But yeah, let's just continue. I is now starting at 2 times points per side, going to 3 times points per side. step size is always the same, we can extract it to a method local variable. Side 3, and that is going to be the left hand side, this one right here. And here for that we are starting at minus, so x is going to be to the left half of the coordinate system, then we're going up from negative y to positive y. From negative, okay, minus side length divided by 2 plus I multiplied by step size. And that is also positive. That really looks bad. Let me just add a couple of debug messages here. Printf render point at x, y, and z. Points I, x, points I, y, points I, z. This should be enough for now. Let's check if those messages are they not even entered? Oh, now they are. Yeah, of course, because I did not add the new lines. Okay, let's have a look at what the printout says. X starts at minus 25, Y as well, and Z is 25. And then X is incrementing, the others are staying constant, which is good. So only the X is incrementing, which is perfectly corresponding to this line down here. Yeah, let's just add the same message in the next for loop as well. Line 1. This is line 1 and this is line, line 2. And line 2 has constant y, constant z, and shifting x again. But that should not be the case. X has to be no, something is wrong there. So that is already good information. What's wrong with x? Yes, of course, it has to start at 0. But we have to enter the point at I plus points 1 multiplied, or actually just points per side. So let's see. Okay, I think these are the two X lines. That's good. Then we have to enter these lines here also at I plus 2 multiplied with points per side. Okay. Something is still off here because we have to start with I equals 0 and it goes to points per side only. Yes, and now this is getting better and better. Okay, let's do side 3 then. Side 4. Okay, side 4, same thing here. Side 4 is going to be the right-hand side. So all we have to do is this. Okay, now the corner is not completed. Not that nice, but let's keep it like that for now. We can change it later. Then let's do, oops. Then we can just copy all of those sides and call them side 5, 6, 7, 8. And side 5 is starting at I multiplied with I plus 4 times points per side. This is I with 5 times points per side, 6 times points per side, 7 times points per side. Okay, and now for all those sides, all we have to do is, well, we're just doing the back side, so that is the side here in the background. So we only have to shift the Z coordinate. Right now it is this plus sign right here, but we can just change it for a negative sign, and that should be it. Yeah, and we don't see the result because the Z-axis is right. If we shift whatever we have by the Z-axis, it's shifted right into the background behind our front side. And so let's do the other 4 sides, the only 4 remaining sides, which are, well, this is 5, 6, 7, 8, and now we have to do, let me do it in orange, these 4. So this is going to be our 9, 10, 11, 12. So side 9. And side 9 is going to be going from negative x to, and from negative y, the x and y coordinates are still, and only the z coordinate changes to I multiplied with step size. Okay, so side 10 is going to be similar, but it's going to be this right-hand side. So this is going to be the side 10 negative side length. Well, it's the same side, just the x coordinate is now positive. That is the only difference. Then side 11 is going to be negative x again. Let's just quickly check. Oh no, in 11 is still positive x, and this time also positive y. And then we have to do side 12. And then it's going to be negative x, positive y. Yeah. Okay, let's see how that looks in a rendered display. And yeah, that's it. The reason we had these scattered points earlier is because there were values in the arrays which were not filled yet. So this is our three-dimensional cube now. It's completely defined if I did not introduce an error here. But since it is not rotated to either side, we can't see the back part of it or the sides. So we are looking at the three-dimensional cube right from the top, basically. And yeah, I think this is a good stopping point for this episode. Maybe let me just increase the side length for a better visual here. I think it's way too small. And I'm 100% sure that there are much better ways to render a three-dimensional cube. And yeah, that's it. Let me just be a bit more generous with the number of points. So we have continuous lines, and that should be, let's say, 1200. Okay, this is our three-dimensional cube now. Now, what's left to do is we have to rotate that three-dimensional cube, and we're going to do that in the next episode. So stay tuned. So far, this is really interesting. It's definitely a challenging one. And the next episode, we're going to have to use math to rotate this. So see you next time. Bye. Now comes the exciting part. We have so far created the code to model a cube in 3 dimensions, but we look at the cube right from the front. So that's why we don't see the sides, we don't see any 3-dimensionality here. And to do that, we have to actually rotate that cube. And to do that, we need to somehow apply some mathematics. And yeah, I think we had a look at this isometric projection, and we could use this rotational matrix here to rotate our 3D coordinates into this typical 3-dimensional view. But maybe we can just rotate it right away. So maybe we can look for 3D rotation matrix and then apply it to our cube points and then see what happens. So this is all for 2 dimensions. Oh, that would be very interesting as well. Just rotate a 2D square. Why didn't we start with that? But okay, we went full all in. Okay, and to rotate around the x-axis, we can use this first matrix. To rotate around the second, we can use this one. And to rotate around y, we can use this matrix, etc. And I would say we should rotate around the... Well, where is it? Ah, it's gone. But for us, I think we should first try to rotate around the y-axis, which is the one that is going straight up. That's the vertical axis in our case. Yeah, maybe. Or we could alternatively also just rotate around all matrices. Yeah, here it says general 3D rotations. Oh, if we calculate this matrix right here, we could figure out, well, yeah, we could rotate this in all directions. That would be interesting as well. Yeah. I'm just thinking on how to actually model this. There should be a 3x3 array. It's a 2D array, 3x3. And the formula might be calculable using some math functions. So let's do that. This is now getting really... this is not really the most interesting part of this entire coding series of the 3D Cube coding series, because this is the heart of rotation. If you ever want to do anything using graphics, 3 dimensions, and you want to do it from ground up yourself, then you have to deal with projections from 3D to 2D, and you have to deal with rotations probably. Yeah, so let's see what we can do now. We have to first define this rotational matrix somehow, or at least define this function. Maybe. Yeah, let's define the matrix. Let's just define it. This is going to be hard. And it's going to be a double. We will use double precision for that. A double matrix, double, and it's going to be rotation matrix. It's going to be 3x3. These are the outer braces, and here inside we should be able to put values like that. I'm just putting dummy values just to confirm that this way of defining a matrix is valid. Okay, if I compile this, it should be fine. Yeah, it is fine. So if we apply the unit matrix, which would be 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1, if we apply that to the cube coordinates, then we should have no change, because this is the unit matrix that keeps all values intact. Maybe let's start with an easier matrix other than this one. Let's just do a rotation around the y-axis. So we have we rotate by an angle called phi. Yeah. Let's just set it to 5. This is just a dummy value. And the first value is cos phi. And for this to evaluate, we probably have to include math.h. But let me just confirm that. C programming yeah, it's part of math.h. Although I don't quite understand why it does not work here. Initializer element is not constant. Aha. No, then let's just create a new function that returns the rotational matrix for a specific angle. How do we do that? We do double 3 by 3 because we know the matrix is going to be 3 by 3. Generate rotation matrix, and it's going to take as argument a double value that we call phi, that is the angle, and I assume it goes from 0 to 2 pi. Okay, so double rotation matrix, expected identifier. Maybe it's not possible to return it like that. So let me just do void apply rotation, and we apply the rotation to a point, and we have to pass that as a pointer probably. And then we specify double phi like that. So we rotate a point around the y-axis by this angle. The rotation matrix is so far so good. And then we have to create the mathematics to rotate this, and it is a simple matrix multiplication, although I'm not sure how to do that in C. So that's going to be interesting now. So we create a rotation matrix. This is a wrong matrix right now, so please be aware of that. And let's do a matrix multiplication that well, we have to loop over the indices of the matrix. We know it's size 3. It's always going to be size 3 because we're dealing with 3 dimensions. We're not dealing with 2 dimensions or 4 dimensions. So yes, it is valid to hard code this value right now. This is never going to change unless you want to change this code to make a 4D simulation, whatever thing. But I doubt that. And then we do another for loop inside here for int j equal to 0, j goes up to 3 as well. Okay, and then we do matrix multiplication in C. We multiply the first row of the matrix. So we access rotation matrix. What is the first row? Is it this index, or is it this one? Oh, it depends on how we define it. But this entry here is the first entry in the matrix, so it would be that. So this is the first row. And in the first row, we access the first element. We are not dealing with the first row right here. We're dealing with all the rows, of course, because it's a nested for loop. I'm just trying to figure out in my head how it would look like for the first row so that I can visualize what I'm doing. So we multiply the values in the matrix, which would be this one. This one would be the first value. And we multiply that with the first value in the point. And that is point. And now point is not a matrix. We have to somehow convert point to a matrix or to a vector to be able to, damn it, to be able to multiply. Yeah, we can do that. Otherwise, we have to do some very odd hard coding of algorithms. Okay, let's convert the point to a vector. I will do it inside this method here. Let's not do too much abstraction. And it's going to be an integer vector. Point vector that is going to be equal to point x, point y, and point z. Let's see if that works out. And then we have to access point vector here at index j. Let's see if that compiles. Error adding symbols. DSO missing from command line. What is that? Okay. Statement with no effect. Yeah, here we have to do something. Apply rotation. We apply the rotation directly to the point. Wait. Let's just first do the matrix multiplication correctly. Double product is equal to 0. Yeah, dot product. Because multiplying the first row of a matrix with the first column of the vector, or the only column of the vector, is practically a dot product. So I am doing dot, so I'm creating basically the dot product here. plus equal to that. Then we have the dot product, and after this we can write the value into a result point. Ah, this code is horrible. Please forgive me. And then result point. No, must be done here. Result point. Oops. No. Result point at index I. Yeah. Is equal to the dot product. That should be okay. And then after that, we have to write the rotation back into the point. So point x is equal to results point 0 y is equal to result point 1 and z is equal to result point 2. Oops. Does that compile? Probably not. No, we still have this one odd error. So let's look for where it's coming from. It's not apparent. I suspect it has something to do with this math library. Let me just delete that statement and see what happens now when we compile. No, still. What is that? Undefined reference to symbol. Huh? Nah. DSO missing from command line. Is this part of the command somehow not working? No, it is working. CCO output is cube. Let's do cube 1. We compile cube C. And these are the compilation flags. Let's re-include math.h because it apparently has nothing to do with that. You should link libm as well when you are dealing with code that uses mathematical functions. If your code, okay, it has something to do with math. You need to link to the mathematics library. Okay, but I thought this would be found somehow automatically. Can I just... I thought this is a standard library. Okay, that works if I use this lm function. Okay, so this is the cube. Nothing has changed. I would like to remove all these log messages. So should I? No, let's keep them. They don't harm us right now. So compilation works. Now we have the cube right here. We draw the points of the cube, but now we also would like, or I would like to try to rotate the cube or somehow do something with it. So let's call the apply rotation function. And maybe we have to do a apply rotation on an array of points. But okay, apply rotation. We provide let's do that. Let's just do a loop. For int I equals 0, I smaller than number of points, I plus plus, and for every point we call apply rotation points I, and we need the address of that. And then we say, I would like to rotate by an angle of 0.5. Ooh, I'm actually getting quite excited now what the result of that is. The compilation doesn't work, but now I've fixed that. I have to draw the points as well after the rotation. Oops. Okay, there's a segmentation fault. Great. Where is the seg fault? coming from. It's very likely somewhere in apply rotation right here. But where exactly? How do I find out where the segmentation fault is? Look at your code around where the seg fault happens. Oh yeah, but I don't know where it happens. Dangling pointers, uninitialized variables or pointers. I'm actually wondering why this is not why it's not just reported here, where the line of the okay, we're dealing with binaries, yeah, obviously. Okay, I will compile using the G flag. Then I will use GDB and try whatever they say here. So let's compile. I will add the G flag. What is the issue here? Okay, I have applied the G flag. Wait, let me clear that. So that compiled. Now what's left is GDB. I should have it, right? No. GDB. Yes, please install GDB. And while this is installing, let's have a look. We run the binary and then we call backtrace. Yeah, okay. Oops. How do I get out of here? Quit. Ah, okay. So we call GDB on the cube. Then we do a run. This ends with the segmentation fault. And it already tells us where it happened. What does happen if I do backtrace? Okay, same message. Cube C line 52. Let me just enable line numbers here and go to line 52. That is this line. Aha, okay. Yeah, that's good news because that's the most interesting line to work with probably in the entire code base. So let's find out where the segmentation fault is here. Dot product shouldn't be it. It's just a counter that is being incremented. The rotation matrix at ij. Ah, yeah, of course. I need to increment j. That's the issue. And that's it. I'm sure it works now. So let's compile. It was really nice to have a first check of the segmentation fault with GDB. Really cool. So let's compile and execute the cube. Okay, and it looks like it rotated. And because we just rotated by the y-axis, we see two lines here. or double sides, but that is because we were looking at the cube. Let me just give you an example. Here's a, what's a good example word? Give me a second. So this is a box right here. And we were looking at the cube at the beginning, right from the front. Now we're looking at it with a slight tilt, but in a different projection also. This is a bad example because you're seeing how things are projected in the camera, and it's a different projection. But anyways, now you're seeing this side back here, and the front side. So we also should rotate it by another X. Oh, sorry, I'm telling you, what I'm telling you is wrong. The rotation matrix is still incomplete. Yeah. So let's do a proper rotation matrix. So we have cos phi here. I'm looking at this one right here, the Y rotational matrix. Then sin phi 1, sin phi. Then there's a 1 in the center because the Y coordinate remains unchanged. Then there's minus sin phi, and then there's, was it a plus or minus? A plus cos phi. Let's have a look, but let's see. Let's just see. Oh my god. Oh, this is terrible. What is that? I think it's time to create an animation, because that animation will tell us how things move. So let's create the event loop. SDL. Let's get an SDL event here. Event. And then do a while, and then let's do an integer is running, a simulation running is true, is 1, and then let's do while simulation is running SDL while SDL poll event, and we poll into event. So we're just creating an event loop in order to be able to animate the three-dimensional cube. And right here we are polling for events. For example, someone quit the window, and then we can close the window. We can stop the simulation and close the window. So that is the point. If we did not do this, then, well, we could create an animation without that, but it would be impossible to interact with the user, and we could not exit the application. So we have to somehow get user events from that. Or to be more precise, keyboard events. Yeah. So and if event.type is equal to SDL quit, then we set simulation running to false. And then we do all of this right here inside this event loop, and we rotate the points by, let's create a value for that, and call it double rotation step, and it will be 0.01. rotation step. Okay. Ugh. Maybe the rotation step is too small. And I can't execute this. Exit because the SDL delay is way too long. Let's do 100 milliseconds. Oh, okay, something is happening. All right. Okay, it looks nice. We can exit the application. And the problem is that we need to create, or we need to fill the surface with black again between each drawing or before each drawing, such that all the drawings don't overlap each other. So let's do that here. SDL, fill, rect, and then we provide a black screen rectangle that is going to, and we're going to, oops, we're going to draw to the surface, and we're going to write in black, color black. So let's define color black up here. Color black. Oops. That should be black. And the black screen rectangle is, we can define that up here somewhere. SDL rect. Black screen rectangle is an SDL rect. And we make it from 0, 0 to screen width and screen width and screen height. So we basically override everything. And I'm using the wrong brace. So now this is fixed. And I have to provide the address of the rectangle and not the rectangle itself. So that is the error that is being complained about right now. Okay, so now we rotate the what the hell is that? Let me do it faster. Faster is better. Maybe the rotation steps are too small, or I don't know. Something that might make sense is to accept doubles here to prevent rounding errors. And then when we draw a point, wait, where is it? Where do we draw the point? Here. Point. No, we draw it here. Yeah, then it is being rounded in the 2D conversion. So that it should be okay. It is not. Obviously, it's not. Which line is that? Line 101. Ah, that's the printf statements. We can fix them probably quite easily. Or we can just delete them. Let's delete them. Printf. Okay, they are gone. Now it compiles. I don't really get this rotation. Is something wrong? Apply rotation. Rotation matrix is this. We have to keep this a double vector, of course. I don't want any rounding errors. Double. Let's see if that changes anything. Yes, it definitely changes something. And this is a rotating cube. Do you see it? This is a rotation by just one axis. Awesome. Awesome. Oh my god. This is really nice. Oh. Maybe it's hard to see because it's not tilted by the x-axis. But this is a rotating cube. And now let's just add the other rotations as well. So this is right now our rotation matrix around what was it? Y? Let's do another rotation matrix. Oh no, let's just create the big one at once. Let's concatenate all the rotation matrices into one big one. This one. This one right here. Let's create this matrix. So we can keep the matrix, but we have to change the entries and we have to change the angles. So we are right now rotating by alpha, beta, and theta. So double alpha, double beta, double, I think it's pronounced that. Yeah, I think it is. Then the first, this is hard to keep track of. Let's delete the whole thing. The first entry is going to be cos alpha multiplied with cos beta. I'm sparing you this. I'm just writing it from a second screen. I don't want to drag it in all the time. So let me just quickly fill that. Cos alpha, cos beta. Then next entry is cos alpha sinus beta sinus. Is it a gamma or a theta? Ah, no, it's a gamma. Gamma. Sorry for everybody triggered already. Sine gamma minus sine alpha multiplied by cos gamma. Okay, I might have to drag it in here. Cos alpha, cos beta. That's the first one. Comma, cos alpha, cos beta, sine. Oh, cos alpha, sine beta, sine gamma. Minus sine alpha multiplied by cos gamma. Then cos alpha, sine beta. Let's do the next entry. Cos alpha multiplied by sine beta multiplied by sine by cos gamma plus sine alpha multiplied by sine gamma. Let me just double check. Cos alpha sine beta cos gamma plus sine alpha sine gamma. Okay, next line. Sine alpha multiplied by cos beta, comma, sine alpha multiplied by sine beta multiplied by sine gamma, over all sines, cos alpha multiplied by cos gamma, no, not comma. Oh, yes, comma. Sine alpha multiplied by sine beta multiplied by cos gamma minus cos alpha multiplied by sine gamma. I think I made a mistake somewhere, but I already know where it is. It should be after the third entry of the first row. This is the second entry. And this is the third entry. Oh no, I didn't make a mistake. I thought I forgot this brace right here. But then I forgot the opening brace. Okay, let's continue with the last line. Sine beta, comma, cos beta multiplied by sine gamma, comma, cos beta multiplied by cos gamma. Closing brace. Why is it this closing brace? Did I forget an opening brace again? I did. Here, and let's add one to the end and a semicolon, and that should be it. That should be the rotational matrix. Okay, that is the rotational matrix. It's not very efficient to compute this every time, over and over, for each individual point, so we might have to extract this to a defined constant later on, but let's just keep it. We can adapt the performance later if needed. Point vector, okay. Then rotation matrix. We have to remove that, and now we're good to go. Now down here where we apply the rotation, we have to provide alpha, beta, gamma. And I will just say double alpha is rotation step. Let's do it explicitly. We can tweak the values then for show later on. Beta and gamma, and we don't need the rotation step anymore. Let's compile and let's execute. Oh, that's awesome. That's so awesome. That's great. Oh my god. Why is this corner here fixed? I mean, it looks awesome. Maybe it has something to do with the values we chose here, with the angle with the angles here. Let me just tweak them to be a bit more random. Let's do something like that. Yeah, that's maybe too fast. How do I best tweak the speed? I mean, it's good to rotate some. Yeah, let's just reduce the frame rate a bit. Yeah, and that is our rotating cube. That's awesome. That's really, really, really awesome. And in the next episode, will we even do that? I think it's really nice like that. It's so nice. I was thinking about whether we should drag it with the mouse, whether we should drag the rotation with the mouse and capture mouse events to rotate this cube. Maybe we will do it in the next episode. Let's see. But this is really cool, especially because we use so much math to solve this problem. And now we just have a rotating cube, and it looks really, really nice. So awesome. Let me just adapt the values one more time, but I'm really enjoying watching these things. So let's do 2 here, 1 here, and maybe 0.05 here. Let's see what the result of that is. Oh, that looks so smooth. It's so cool how this turned out to be. Awesome. Awesome. Yeah, so if you enjoyed this video, please stay subscribed. There's so much to learn. I'm a complete nobody when it comes to programming these kinds of things, and probably my code is full of bugs and full of hacks, but this is the result from just 2 hours of sitting in front of the screen and focusing on a problem, and this is just awesome. So if you enjoyed this, then please leave a like and see you next time. Bye bye.